So the way we started definite integrals was finding these areas like this. So you can expect some sort of picture with some sort of part circle and triangles and so forth, where you can actually calculate exactly what that area is using geometric shapes. Okay, that's also in section 1 where we talked about how you can split up integrals. So you may have something like that, where you could do the remember the integral, we're talking about the integral from a to b is equal to the integral from a to c plus the integral from c to b, right? Remember, that's why I picked that, because c is not even between a and b, but it doesn't matter. It doesn't matter. As long as what's up here is the same, and then your beginning is here and there, it doesn't matter that it's not in between, okay? And we had some of them in 61, 62, 63, kind of went through those again the other day. But so that thing was splitting integrals, but we want to be able to find with some geometric shapes, we can find that area. Now, approximation is not something we're really going to be working on right now, okay? So I wouldn't worry about this. That's something we're going to go into in chapter 6 more into, okay? Right now, we're going to focus on this part here. So if it's not a geometric shape, you can probably expect that on the quiz to be doing some of the fundamental theorem part 2, where we find areas with the antiderivative, right? So that's kind of bookend here. We started off doing areas that were definite integrals, areas that were geometric shapes, okay? And then we ended with finding areas with the antiderivative, doing the fundamental theorem part 2. In between there, we had to get from, an area down to an antiderivative, and that's where fundamental theorem part 1 came in, and that's where we did the whole thing with area functions and the chart stuff and the connection, all that cool stuff. You're not going to have to draw those areas and find those areas as a function, but you want to be able to do all the chart connections like today's homework had on it. And then, of course, remembering when you change that left edge, that just changes the C value, that kind of stuff. Okay? All right, so that's kind of the big picture of the stuff that's on the quiz. What problems did you want to talk about on the homework? Which page?
I think it was
5.3. So 5.3 is where, okay, now we've 5.2 was all about the aha moments, the oh my God, I can't believe the area is giving us the antiderivative. Wow, what a connection. And then 5.3 is where we call it the fundamental theorem of calculus, part 1 and part 2, and that's where we can actually use it then to start finding these things, okay? So 41. Okay, so this is your chart kind of stuff. So let me see if I've got this picture somewhere.
it's like 49.
49?
Yeah.
Okay. Let me check out my... See if it's got it. No. Well, that's 41, which we can look at, but you said it's not 41. You think it was actually 49?
Yeah.
You were questioning. Okay, so let's go with that. Okay, so on 49. So 49 says, let big F of x. So yeah, there's going to be some questions. The 5.2 questions are going to be about the chart. They're going to be about notation, being able to handle the notation. Actually, 5.3 a little bit. This one's in 5.3, but it's more about what we learned in 5.2 actually. Let big F of x equal the integral from 0 to x of the cube root of 1 plus t squared dt. Right? Find the derivative of big F of x squared. Right? Is that what it says? Okay. There you go. Ideas. Put an x squared in here. that's really close. Now, and then just write that, you mean? Because the derivative of big F is little f. So are you saying the answer is just that?
And then do
Of what?
that.
This whole thing? Not quite. Not quite. You're on to the right track, though. But why? But here's why I would say you don't do the derivative of this. Because isn't this little f? Because if you do the derivative of that, you're doing the derivative of little f. They're telling us to do the derivative of this. Closer. Leave it like this. Not quite. No. Okay, now, one of the things I told you that I will have you do, fundamental theorem part 1 says this right here. It doesn't matter what I put here, I can put a 2 or whatever. If I have this right here, right? Right? What is the answer to this right here? Little f of x is the answer to that right there. That's what the fundamental theorem part 1 says. Why is that? Pretend this isn't here. What do we think of when we see this? We've been away for a few days now. What do we think of when we see this? Starts with an A. Antiderivative, right? Antiderivative. That's what the area function is, right? That's what the area function is the antiderivative of this. So call it big F, big A, big G, big H, I don't care what. It's the antiderivative. So it's the antiderivative of F. And then when you do the derivative, what happens? Goes back to little f, right? I mean, they cancel each other out. And what about this 2? What's the 2 effect? The plus c, right? The plus c. So forget this. This would be the antiderivative, right? The antiderivative plus some c, but when you do the derivative, what happens to the plus c? Goes away. So it doesn't matter what the 2 is down here, right? So it's little f. It's little f of x, right? That's what that is. So that's kind of what we're doing here. Okay, the difference is we got this thing on the inside. Okay? So you're right, there needs to be an x squared plugged into there, but okay, how about we do it this way? How about we do it this way? Pretend you didn't even see this up here. Just ignore that. And only look at this. Because I swear to God, a week and a half ago, or 2 weeks ago, when we were doing the midterm and we hadn't learned any of this area stuff, if I would have just written this down and asked you what to write, what do you think you would have done? What would you have written?
2x.
Big F or little f?
Just 2x. Just big F.
Big F prime. You got to do the derivative, right? It's a derivative of the outside, right? With the inside left alone, times 2x, right? Derivative of the inside. Now, what's big F prime? What's another name for big F prime? Little f, right? So this is little f of x squared times 2x. Okay, now let's bring in this thing. Where's little f in this? Little f is this part, right? So what's little f of x squared? Oh, that's plugging x squared in there, right? So I agree. So you guys did that part right here, right? But what'd you leave off? There needs to be a times 2x, right? Because that's what this is saying. Okay? Now, what I thought somebody might say is if this is big F of x squared, wouldn't that be like putting an x squared right here? Wouldn't that be like putting an x squared right here? Now, I'm not going to have you do this on the quiz this time, but sometimes we see this on the test, on like the AP test. They'll do this to you here, and then they'll do, oops, that didn't go inside there. And then they'll do this, right? It's kind of like what I told you I'm going to have you do, except they don't put an x here. They put like an x squared or something else up here, right? Well, all you do Remember we said that the answer to this is just little f, but you put an x in there instead of the t, right? You put that x in there. Well, it's the same thing here. All you do is you put that in there, right? You just put that in there, but then you have to tack on the derivative of that, the 2x. And we can just see why, because it's this right here. It's just the old chain, right? So if I gave you something, so 49 is basically telling you, like, if I gave you something like this, 3 to the sine x, right? And then I gave you some weird looking square root of 1 plus 2t or something here, right? dt. What's the derivative of that? Well, it's just that with sine x plugged in, and then times cosine x. That's all. That's what you would do there. Okay, we're not going to get into that. I like the way they wrote it because it definitely looks like that product rule. So bottom line is, though, what you need to know for tomorrow, when you see an area function, something to the x, 0 to x, 2 to x, 4 to x, whatever, that means antiderivative. That means antiderivative. When I do the derivative, they just cancel each other out. I get that. Okay? I mean, while we're on that one, let's just talk about notation, okay? Let's just talk about notation, all right? Because one of the things I want you to be able to do on a simple one, if I give you this, right? Let me just give you a real easy one. Let's say we had 2 plus t squared. I don't know, let's do a real easy one. dt. And I called that big F of x, right? And I said I wanted you to write a formula for big F of x, right? I want you to write the formula for this. What would you do? This is, okay, now you're thinking of, okay, that's interesting that you said that. I wasn't going to go that way because he's thinking of fundamental theorem part 2. Now, we only said fundamental theorem part 2 was when you had A to B, when you had a definite, right? But it actually kind of works. But before I do that, I don't want to get too confusing here. Let's just talk about this in terms of how we did it. What do you think of when you see this? Antiderivative. Antiderivative. What's the antiderivative of this? Right? When it comes, this is little f, but when we do the antiderivative, when it comes out here, we got to put in x's, right? Not t's. So it'll be 2x plus 1/3, not t, x cubed plus c. Now, how do we take care of the c? We got a free initial condition, right? We know f of 3 is 0, right? So if this is just a simple little function in here, I call it big F, we can do the antiderivative, right? We can tack on a plus c, right? This is where we would draw this. Remember, this is where we drew it and then we did all that area formula. We're not doing that, right? Because we know it's the antiderivative. So I would just want you to do the antiderivative with a plus c, do your free initial condition. So this would be 6 plus 1/3 times 3 cubed would be what? 9. 27 times 3 would be 9. Plus c equals 0. So this would be 15 plus c equals 0. C would equal negative 15. So this would be 2x plus 1/3 x cubed minus 15. That's what big F of x would equal. Are you with me? Right? Now, what if I told you to do the derivative of that? Well, the derivative of that would be 2 plus x squared. And what would happen to minus 15? Be gone. Oh yeah, we knew that, right? The derivative of the antiderivative, they should cancel each other out. You should get 2 plus x squared, right? I mean, so we knew that's what should happen, right? So if I gave you a problem like this and said do the derivative of this, that's where we said, well, it doesn't matter. It's just going to be 2 plus x squared, right? Because the derivative and the antiderivative cancel each other out. But if I just wanted what the antiderivative was, we could do that, right? Now, Max said something interesting. Max said he was looking at this and calling that big F of x minus big F of 3, right? Now, it's a little bit confusing to do that because big F of x was supposed to be this, but now you got big F, you know what I mean? So but I'm okay with that. And you'd be saying, well, big F of x means do the antiderivative of this. So that'd be 2x plus 1/3 x cubed, right? And then minus and then plug a 3 into that, right? A 3 into the antiderivative. Well, we just said the antiderivative is 2x plus 1/3 x cubed. And so let's plug a 3 into that. That'd be 6 plus 9. 6 plus 9 is 15. Oh, look at that. 2x plus 1/3 x cubed minus 15, same thing. So it does work to actually do that, right? To actually think of this with this fundamental theorem part 3, where the big F of x is just the antiderivative, and then that's that. So that's okay. So if I tell you to do that, and you work it with the free initial condition like we did, or you do it this way, it's all good, right? It's fine, either way. Okay, so that's some of the stuff from section 2 I'd want you to be able to do with the notation, just under, again, can't say enough. What do you think when you see this? What do you think when you see that? Antiderivative. Now, I might give you one, though, like this, where, I mean, forget the rest of this down here, forget all this, but I might give you this. You can't do the antiderivative of that, right? But if I tell you to do the derivative of this, what are you going to write for your answer? If I tell you to do this right here, what's your answer going to be? Oops, no, that's not right. Cube root of 1 plus x squared. That's all you're going to do. You're not going to plug in the 0. You're not doing, no. It's just the derivative of the antiderivative. They just cancel each other out. It's just that right there. That's it. It's cube root of 1 plus x squared. See, because you can't do an so sometimes you get something here you can't do the antiderivative of. Well, I'm not going to ask you to do the antiderivative, right? I might ask you to do the derivative of it. Well, the derivative of the antiderivative just goes away and you end up with that. Okay, but on this one, I actually wanted the antiderivative. I wanted to know what big F was. Okay? All right. What else? Homework.
On 26 and 28, is that just like 1 over x being there?
Same page?
Yeah.
Yes. So, you are going to have to do some simple fundamental theorem part 2. When we go back to this page here, you're going to do some of this, right? So, you got to be able to do some basic antiderivatives. And so,
Is that like 26 and 28?
Yeah, turn to page 333 real quick. Turn to page 333 real quick. Those are just a few of the basic antiderivatives we should know. But now, the answer to your question is, yes, on 26, I would definitely not write that dx up on top like they do, right? I would definitely write it like this, okay? And the same thing is true on 28. Okay, so let's talk about something really important here when it comes to antiderivative. What is the antiderivative of 1 over x? Natural log of x. Now, it turns out that when we learn about this later, for the rest of this week, we're going to put absolute value bars around this. Okay, we'll talk about why they need to be there later, but right now, don't worry about it. And I want you to do your right bracket notation. Some of you guys, when I came around and looked at your homework, you didn't all have this written out. I want to see this written out. It's no calculator. The quiz tomorrow is all no calculator. Okay? We don't need it for any of this. Okay? So, when I do this antiderivative, I put in the right bracket, and then I do my f of b minus f of a, meaning because this is my big F right here, right? So now, big F of b minus big F of 1. You don't have to write that out. That'd be ln e minus ln 1, right? And ln e is 1, ln 1 is 0, so the answer to this is 1. Okay? So I want to see this. I want to see this written out tomorrow when we do this, okay? Now, when we look at 28, so 28 says the integral from, what is it, -2 to 5 of 1 over x plus 3. dx, yes, just put that, when there's a dx on top of the fraction, just take it off and move it off out to the side. This is also ln x plus 3, right? Because the derivative, you just test it with the derivative. We're just doing simple antiderivatives. We're going to get into harder ones as we go on to the gateway test. But just test it. Do the derivative. The derivative of ln x plus 3 would be 1 over x plus 3 times the derivative inside, which is just 1. So it's ln x plus 3 from -2 to 5. And so then this would be ln 8 minus ln what? 1, and ln1 is 0. I want you to simplify it. You got to know ln1 is 0. So this would be ln8. Now, if you want to leave it ln8, I'm fine. If you did this one on your calculator, it wouldn't say ln8. Your calculator would say 3 ln2. Why would it say 3 ln2? Because that 3 can go up there, right? And that's 2 cubed, right? ln8 is 2 cubed. You can bring the 3 down front. So if you did this on your calculator, it would say 3 ln2. But I'm okay with ln8, okay? But if you change it to 3 ln2, that's fine, okay? But it's no calculator. So, but you do need to know that ln1 is 0, lne is that, okay? Now, here's where people make horrible mistakes. Because then I'll see people, well, okay, first of all, what's that antiderivative right there? That's 4 ln x. That 4 doesn't matter, right? I mean, it's like, remember we said you can pull that out in front, right? We talked about how if you have a number in there, you know, a constant there, you just pull it out, okay? So that would be 4 times ln x, okay? So the 4 on top doesn't really matter. What if it was a 1 over 4x? Now it's just 1/4 ln x, right? Because this is just like a 1/4 pulled out in front, right? It's just like 1/4 times 1 over x, right? So just do that, okay? Now, with that said, here's where people go terribly wrong. How are you going to do that antiderivative? It is not ln. It is not natural log. Yes. Only thing that is natural log is when you have x to the first, or like in this one, if you do a shift, that's just a shift of x to the first, right? So if you have x to the first only on the bottom, that's a natural log. If you have any other power, then it's a power rule. So what you'd want to do is you'd want to rewrite this as x to the -2, right? And then you'd want to raise it up 1, which takes it to what? -1, and then divide by -1, right? So if there's any other power down here, it's not a natural log. Only when it's 1 over x is it a natural log, okay? So then this would be what? That'd just be negative. I mean, we bring that up top as is -1 divided by -1 is the same as times by -1, and then over x, and then that's from, and then this would say this was 2 to 4 or something like that, right? 2 to 4, so that'd be -1/4 minus -1/2, and then you should simplify that, right? So that'd be -1/4 plus 2/4, that'd be 1/4, right? Like that, right? So if it's any other power down at the bottom, you make it a power. Okay? All right. Any others there? So that's, if we go back to our quiz review, so that's this fundamental theorem part 2. That's doing this kind of stuff. You're also going to do some things with this. We've talked about our notation here, notation stuff. We talked about swing intervals. The chart stuff. Any problems with any of the chart stuff, like 1 through 8, or any of those things, 19 through 30, 19 through 30 was the antiderivatives.
Like, if it's asking for like a minimum or a maximum over the entire interval, sometimes I don't like know how I'm supposed to.
Give me an example. That was like a 30.
This would have been one of the like chart ones where they gave us the graph. And
that would have been like this one here.
Yeah.
Yeah,
I know
okay.
how to find like local, but then how do you know what would be the.
Okay.
What?
They never asked.
Sometimes it will say like what's the absolute.
37
number or
does.
something.
37 did. Didn't you have to do 37? 37 did, I think, is what you're kind of talking about. So this says the big F, is it big F? Big F is the integral from 0 to x of little f of t dt, right? And this is little f right here, right? So 37 says, at what value of x does big F attain its minimum value on the interval 1 to 10? So starting here to here, right? Now, I like an area argument here, okay? But we could use because remember, what do we know? Big F prime is equal to little f, right? Whenever you see this, I think that's a good way to write that. The derivative of big F is little f, okay? So, when they want to know where does big F have its minimum value, so this is the area from 0 to x, right? So the area from 0 to 1 is going to be some I think starting to draw a graph's not all bad, right? The area, so when x is 1, right? That would be the area from 0 to 1, right? So that would be this piece of area right here. So there would be some positive area like that. And then what's going to happen? It's going to pick up a bunch of negative area, right? And it might even go all the way, that looks like more area than was here, possibly, right? So it's going to probably go down, 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 and probably get into the negative here a little bit by 3. Then what? But it's only going to be a little bit into the negative, right? Because remember, big F of 0 is 0. We know that, right? Big F of 0 is 0. So from 0 to 1, it picks up some positive area, right? But we're only wanting the minimum from 1 to 10 out here, right? Okay? So it's going to go up at 1. It's going to have the area from 0 to 1. So that's that area. It's going to pick up some negative, which is going to maybe even more than offset that. So it's going to be down here by the time it gets to 3. Then what's it going to do? It's going to pick up some positive area. But how much? Not as much as it lost here, right? It's not going to pick up as much because this is a smaller piece than this, right? So it went down, down, down. It's going to come back up, but it's not going to go up as high, right? Now, what's it going to then do? Negative area, but how's it compared to that? This area is smaller than that, so it's not going to go back down as far as it was here, right? It can't. And then it's going to pick up some positive area, which means it's going to come back up, but not as far because it keeps picking up smaller and smaller chunks. And then it's going to go back down just a little bit. You know, whatever. I don't know that it'll be right at 0, but doesn't that have to be its minimum at 3? Right? So if you kind of drew this and used that, talked about that area argument, you could do that. Then the other thing you could do is if you talk about slopes, right? These are the slopes of the big F graph. So starting at 1, negative, 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 negative for quite a while. So it goes down, 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 down. Then it's positive, but not as much as it was negative. You know what I mean? So the slopes talk just about the same as the area. So that's kind of the discussion. Okay, that's kind of the discussion. Okay, local, yeah, 35 and 36, like you said, that's easy. Are there any local max? Does big F have local max? Yes, big F has local max when big F prime, or F, changes from positive to negative, right? When little f changes from positive. So there's a local max, there's a local max, there's a local max, right? And remember what we talked about though, local max, when little f goes positive to negative, big F is going to change from increasing to decreasing. You should say all that, right, when you're doing local max and min. But that's just chart stuff. When little f goes positive to negative, okay, but make sure you've written this down. Right? Because you technically can't answer a big F question using little f. You got to use a big F question using big F prime. Well, big F prime is the same as little f, so as long as you've said that, you're good. Okay? All right, what else? Any other chart kind of questions or any of those things? Any of the homework at all? Because it's all the kind of stuff that could be on quiz. Well, I know you've got at least one more question because I looked at your papers. Yeah, 48. Because some of you did not have very much on 48. Right? I know you had a question about 48. Now here's what 48 says. 48 says, okay, on the one hand, you've got the derivative of the integral a to x, little f of t dt. And you're supposed to show that that is not equal to the integral from a to x. And then in here is the derivative dt of f of t dt. Now, what is this right here? Derivative of little f. Isn't that just f prime? Isn't it? Right? So we're supposed to show that these, now what is this right here? Isn't that just little f of, no, x. When it comes out of there, it's got an x in it, right? This is fundamental theorem part 1. This side is fundamental theorem part 1. That's it, word for word, right? I mean, letter for letter, that's it. The derivative, this is the antiderivative. Basically, this is saying this. This is, you know what this problem is? This is square root of square. Is the square root of x squared the same as the square root of x squared? It's about the order you're doing it. Look at this. This is saying, is the derivative of the antiderivative the same as the antiderivative of the derivative? That's what it's saying. Does it matter what order you do them? Well, let's think about it. If you do the antiderivative, you're going to add on a plus c. Then you're going to do the derivative. It gets rid of the c. So let's say we started with 2x. And we do the antiderivative. You get what? Take it back. Let's start with 2x and we do the derivative. And we get what? 2. And now let's do the antiderivative. And what do you get? 2x plus c. Okay, now let's start with 2x again, but this time let's do the antiderivative first. What do you get? Now let's do the derivative. Do you get the same thing? No, because when you do the antiderivative last, there's what on it? A plus c. So they're not equal. It said unless little f of a, it said assuming that little f of a is not 0, right? Because if your c, if that's your plus c, if your plus c is 0, then they would be the same, right? But if the plus c is not 0, they won't be the same. Now, because look at this, I would use Max's. Here's how I would show this. I would do Max's thing right here. So this side we know is little f of x, right? This side, that's f prime of t. Now what this says, do the antiderivative, right? Well, what's the antiderivative of little f of f prime? F. But it would be f of x minus plus c, or we could write, if we do your thing, fundamental theorem part 2, it could be f of x minus f of a. That's like the plus c. It's kind of where that 15, remember that this 15 came in here, right? It's like the plus c, or it's the 15. So it's that same thing. So these are not equal unless f of a was 0. If f of a was 0, then yeah, they'd be the same thing, right? So that's all that was saying. Is the derivative of the antiderivative the same as the antiderivative of the derivative? Well, it turns out no, because of the plus c, unless the plus c is 0. Okay? So that's just about notation. So I could ask you a question like that, something similar, you know, about that, just getting at the notation. So that, I mean, there's not really, you can't really study for that other than just understand what, you know, this notation is saying. But there's going to be plenty of these other problems that are just kind of straight antiderivative problems like this, or the chart, just basic chart problems. Going to be some of that. Definitely going to be some area, so you're going to have to be doing some triangle areas and some rectangle areas and some circle areas, you know, and stuff like that. Plenty of those kind of things. It shouldn't be that hard of points to get. Okay, anything else? Yes?
What kind of problems are you talking about for splitting?
For splitting, okay, good question. So, well, that would probably be like, if you turn back to, well, that's not as good. Let me see here. How about this? Let me make one up. I don't know that there's a good, I know we did some, kind of did those, but we didn't. How about this? How about if I told you that the integral from 2 to 5 of little f, actually we did those. That was back in section, yeah, that was back on page 313 41 through 46. And they told you this. They said the integral from 2 to 4 was 7. They told you the integral from 1 to 2 was -1. And they told you the integral from 0 to 2 was 2, like that. Okay? And so then they ask you, okay, what's the integral from 0 to 1? Right? What's the integral from 0 to 1? Well, the integral from 0 to 2 is 2. The integral from 1 to 2 is that. So using that formula for splitting integrals, remember 0 to 1, this has to be your beginning and your end. Well, that would equal the integral from 0 to 2 plus the integral from, now careful now, 0 to 2 plus 2 to 1, right? Remember, on that formula, so back on this formula, remember what has to be here. Those, right? Those have to agree. This has to be your beginning, that has to be your end, and then those in there have to be the same. So if I want to do 0 to 1, I got to start at 0, end at 1. And then in between here I have this. Well, what's 0 to 2? That's 2. And what's 2 to 1? Well, that's the opposite of 1 to 2. Well, 1 to 2 is -1, so -1, so minus a -1 would be +1, so 2 plus 1 is 3. That's what I was talking about. Okay? Oh, I know what I was going to talk about. What if, this is another thing we had at the very beginning of our lesson on this. What if I told you the integral from 0 to 5 of f was 6, and then I asked you for the integral from 0 to 5 of 3f of x plus 2. That's the other thing I meant by splitting the integrals.
Oh, you could do like the integral from 0 to 5 of 3f of x and the integral from 0 to 5.
And you can pull the 3 out of that one, plus the integral from 0 to 5, right, like that. Is that what you were saying? So I can split that as 2 different integrals, here and here, right? Now what's this one? 18. And what's this one? 10. Well, what's the graph of 2 look like? Right? From 0 to 5. 2 times 5 is 10. Right? It's not just 2. Right? That's not 2. It's the area under 2. Right? It's the area under 2 from 0 to 5. You could also think of this as just shifting up 2. We talked about that, right? If you shift the graph up, what happens? You gain a strip of area that's 2 tall and 5 wide, right? Is 10. So 18 plus 10 is 28. So if the area from 0 to 5 is 6, and I give you this, that's the other thing we did, splitting it up. And that was something we did the very first day, very first assignment. So if you go back to the 5.1 homework, there was some of that. It was on, that was like 23 through 28. That was page 312, 23 through 28. There was some of those. So if you want to go back over those too. So that was just, yeah, that was just some of that split up stuff. Okay. Good questions, Kevin, because that will definitely be on. That's what I meant by this.
How did you get 18? Is this the triangle?
No,
You have no idea what happened.
the integral from 0 to 5 is 6.
Oh.
Yeah, you were given that. So that's why it's 3 times 6 is 18. That's what I came from. Yeah, I should have wrote that. Thanks. Yeah, so you had to be given that.
Will you take off points if you left out the D of X?
Well, I can't think of any times you're actually writing the integral necessarily. So I don't think that's like when you split it or something. No, that's not really a factor. Okay, all right, so let's do this. Just as a little more practice on antiderivatives, let's spend a little time here in the LH packet. I didn't assign that. It's 3 through 36, multiples of 3. Now, I'm going to stop you here in about, 20 minutes. But this is just big F of B. All this is big F of B minus big F of A. So it's a very small part of what the quiz is about. But it's fundamental theorem part 2. That LH packet, it's the same page we were on. No, I take it back. It's page 298. That's what it is. Page 298. So it's the next page. Then it goes over to the other one a little bit. But it's just doing the antiderivative. So the first one is an example, 0 to -1 to 0, x minus 2 dx. So we would do the antiderivative 1/2 x squared minus 2x, right bracket, -1 to 0. We would put in 1/2 0 squared minus 2 times 0. I know that's all going to be 0. Minus, but remember I talked about how important these parentheses are. 1/2 -1 squared minus 2 times -1. We work that all out. This would be 1/2 plus 2. So that's 2.5, I think. And so the whole area ends up being that's what I'm talking about doing here on this LH packet. Okay, so that's number 3 on page 298. Big F of x, A to B, and then it's just big F of B minus big F of A using the antiderivative. Okay, and again, I'm going to stop you here in about 20 minutes, so go ahead and try to get a bunch of those done if you can. I've got the answers. Let's see, the answers to the LH packet is, I don't know if I ever pulled that out. This book's falling apart, so be careful. This is the answers to the LH packet. So if you want to check them out as you do. Now sometimes you have to. All right, so we've got the quiz 5.1 through 5.3. We reviewed all that stuff. These problems you're doing here in the packet. Some of the harder ones you were having questions about, or some of the ones, you were having questions about. You're not going to get too terribly difficult on the quiz tomorrow with that antiderivative, F of B minus F A. A few of those, but the main emphasis is more, the splitting the integrals, the antiderivative area function, the plus C ones. Some of the stuff we did more towards the beginning of the period. Rewatch the video for the beginning part, if you want to, as part of your study for tonight. Wouldn't be a bad thing, as you look at it. Because we are going to go on to something here that's not going to be on the quiz, but I want to get us kind of a head start on that. It doesn't take a whole lot of time for you to be able to start practicing them. So after the quiz tomorrow, some of you will get done fairly quickly with the quiz. There'll be plenty of time. I want you to have some work time at the end to start practicing these as we get ready for our gateway test. So as we move past tomorrow's quiz, we're talking about antiderivatives. We're talking about obviously, if one of the nice ways for us to be able to do an area, a definite integral, is by the antiderivative. We better get good at doing antiderivatives. Now, some basic ones would be like these on the screen. So now, notice that I've written here the word indefinite integrals. Now notice my integral is missing what? The A and the B, right? Now we're going to talk more probably on Wednesday, well, not on Wednesday, I guess we don't have school on Wednesday, no. normal school, I guess. So I guess on Thursday, so I said that assignment was for Wednesday, I guess it's more for Thursday, actually. So on Thursday, we're gonna talk more about why this integral sign doesn't have the A and the B on it. But basically it means this. If you have an integral symbol without the A, without any numbers on it, it just means do the antiderivative. That's all it means. Do the antiderivative, just stop. So you have a plus C on there. So it's kind of like when we have the something to the X or whatever, right? So basically for right now, if it doesn't have the A and the B on there, then it's an indefinite integral. And that basically means just do the antiderivative. So for this one, your answer would be, what would be your answer for this one? 1/3 x cubed plus C. And on this one, careful now, it's negative cosine x plus C. This is what your gateway test is going to look like. 10 problems on a page that look like this. Now there will be a couple on there that will be definite integrals where you have to find the f of b minus f of a. But a lot of the gateway test will just be this. Do the antiderivative, right? Now people will say, what happens if I forget the plus C? Well, I'll remind you. I'll say, don't forget, put plus C on there.
This usually go better than
It's pretty similar. It's pretty similar. All right, so let's say we had one like this. Now, we don't have a lot of time, so I'm not going to give you a chance. This would be something like, that could be on tomorrow's. Now, tomorrow's is more about definite integrals, but if you get one, if you get a function that's got 4 terms in it, right, you just do the antiderivative of each term. What's the antiderivative of 3x to the 4th? 3/5 x to the, and I don't care if you write this down or not, you probably don't even have to right now. We're going to come back and we're going to look at this one again probably on Thursday. So 3/5 x to the 5th minus 1/3 e to the 3x. Remember, e to the 3x is its own derivative, but you got to kick out a 3 when you do the derivative. Well, so when you do the derivative of this, you're going to kick out a 3. There better be a 1/3 sitting there to cancel it out. Okay? We already did this one earlier today. What's 1 over x plus 3? ln. Now, we're going to learn later here in a few days why there needs to be bars around the x plus 3, but I'll just put them there so you understand. And what about this guy right here? No?
X to the
No. Arctangent of x. And then plus c. Because what's the derivative of arctangent? 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared has to be arctangent. Now, you notice here I said page 333. That's on page 333 has a list of antiderivatives we just have to memorize. One of them's like 1 over x and so forth, so on. But we'll get into all that and be studying that a lot more later on. Here's the one I really want to talk to you about right here in the last 8 minutes that we have. So what would be the derivative of sine of x cubed? What would be the derivative of sine of x cubed? Cosine of x cubed times 3x squared. And we would usually rearrange that. We'd write 3x squared and then cosine of x cubed, right? We all okay with that? The old chain rule, right? Well, doesn't it make sense then that if we were going to do the antiderivative, then it would be the derivative of sine x cubed is this. Doesn't it make sense that the antiderivative of this should be sine x cubed plus c? Right? Doesn't it make sense? It's got to be. That's the whole point of an antiderivative. This is the antiderivative. That means the derivative of this should get us back to that, right? So now the question is, how in the world could you have looked at this and known that that was going to be the antiderivative? Right? Well, remember just a minute ago when we said you'd have to kick out that 1/3 on that e because there was stuff on the inside? Wasn't that the same problem? You got some stuff on the inside here. So here's how you would look at this. You would look at this and you'd say, oh, I got some stuff on the inside. I got an x cubed. So that means when I do the derivative, remember you always, when you do the derivative, you leave the inside alone, right? So that tells me this inside is going to be there in my answer. There's going to be this x cubed on the inside. But when I do the derivative, I'm going to have to kick out a 3x squared. Oh, nice. I got a 3x squared sitting right here. In other words, if I have an x cubed on the inside, if it's going to work out nicely, I better have a 3x squared sitting here. If I don't, it's going to be a problem, right? It's going to be a problem. So it turns out that this is actually nice that I have this here. So how are we going to work that? So let's say we have this problem right here. This is the one I'm just talking about, right? So we had integral 3x squared cosine x cubed dx. So let's say this problem was staring us in the face, right? We already know what the answer to this is supposed to be, right? The answer to this is supposed to be what? Sine x cubed plus c, right? That's what the answer is supposed to be. Here's how we're going to look at this problem. This is called U substitution. U substitution. Now, the few problems I'm going to give you as homework are going to say, they're going to tell you what to let the U equal. When I say let the U equal, that's what we're going to do here. We're going to say, all right, I'm going to let U be the inside. That's almost always what we let U be. If there's something on the inside, we say, let's call that U. Let's call that thing on the inside U. Okay? So we're going to let U equal x cubed. Now, we're going to do the derivative of U. We're going to do the derivative of U, but I'm going to write it this way. I'm going to write du over dx. That's U prime, right? Derivative of U is U prime, but I'm going to use this notation. Du over dx, and what's that? 3x squared. Now, I'm going to do a little trick right here that we haven't done before, but we're going to do now. And I'm going to take that dx, and I'm going to move it over to this other side. Does that make sense? Does that look reasonable, what I just did there? Does it look reasonable that I can move that dx over to that other side? Because I want to keep the x's with the x's and the u's kind of by themselves. Okay? All right, now, the name of it is U substitution. So what I'm going to do is I'm going to take and substitute and make myself a new integral, except my new integral is going to have u's in it, not x's. So, look at this part, look at those two things I've underlined right there. 3x squared and dx. What can I replace those with? Couldn't I replace those with a du, and the du always should go at the far end, right? So I'm going to put that way over there at the end. Doesn't that make sense? Okay, and what about this thing in here with the double underline? Couldn't I put a u there? And what about the cosine? Oh, I'll just bring it along. So this is cosine u. Doesn't that make sense? Look what I just did. I substituted everything out. Now, what does this mean? This means do the antiderivative of this with respect to u, right? Remember the du means with respect to u? What's the antiderivative of cosine? Just sine of u plus c. Oh, but wait, what's u? So let's put the x's back in. And voila, there it is. Make sense? So I saw this messy problem. Now, all the ones you have for homework, they're all going to set up very nicely. And they're actually going to tell you what to let the u's do. Okay? But what did I pick? I picked let u equal the thing on the inside. So the key to the thing was I let u equal that. Then I did the derivative of that. And then I moved that x over. And then I said, now let's just replace all the x's. And let's put their equivalent u's in there. And then we do it, and we got it. It's called u substitution. Okay, in section 5.4, now this is really not due until Thursday, so I'm going to add on to it tomorrow though. So if you want to try it, but your first focus should be getting, practicing for the quiz tomorrow, and this will not be on the quiz. Okay, so your first focus is rewatch the beginning of the video maybe or whatever, practice for the quiz, finish those LH ones a little bit, but be ready for that, and then we'll be moving on to this U substitution. Because use substitution helps us do functions where there's stuff on the inside. Well, it's kind of like chain rule. It's kind of the reverse of chain rule. Well, think about it. Chain rules, probably the most common thing we do with derivatives, when we have stuff on the inside. So use substitution is probably your most common antiderivative technique as well. Now, there's going to be other techniques we're going to learn, but probably use substitution is one of the main ones, right? I would say if there's 10 questions on the gateway test, 5 of them have use substitution, right? Some are probably basic, just straight antiderivatives, like this one, right? Probably a couple of those. And then there's some other techniques we'll learn too. Okay? All right.